Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our third day of notes from Chapter 17. And what we're really looking at today is other buffer information, the second half of Section 17.2. Now, we already looked at what is a buffer system, how do you calculate its pH, what pH range does it protect, and so forth. And we talked about neutralization and how it doesn't change the pH by much until the ratio is off by a factor of 10. But we never really talked about how to do that calculation. So that's really all we're looking at today is that part. And you need to understand there's two parts. There's the stoichiometry part where you're looking at the neutralization to find out what the new concentrations of our conjugate and its, or of our acid and its conjugate, of our base and its conjugate. And then the equilibrium part. And one of the things you need to understand is it's safe to assume that all of the strong acid or base that we're adding to neutralize a little bit our weak acid or base is going to be 100% consumed. So all that's going to be used up in the course of the reaction. So there's none left over that can affect pH. Now, there's really two parts to the calculation, and it doesn't matter whether we're adding OH minus from a strong base or whether we're adding H plus from a strong acid. In each case, we're going to do the same thing. We're going to determine how the neutralization reaction affects the amounts of the weak acid and its conjugate. And then from there, we're going to use the equilibrium expression to calculate the new pH under those conditions. So really, it's a two-part process, the stoichiometry part and then the equilibrium part. So here is an example of a buffer problem. So notice we've established an equimolar buffer. We've got 0.300 moles of acetic acid and the same amount of sodium acetate in 1 liter. And it tells us what the pH of that buffer is. So remember, that's the equimolar amount. So if we just take the, well, we'll get to that in a second, deals with the Ka. But what they're asking is, what is the pH after we add a little bit of NaOH to it? So that's the situation. We've got an equimolar buffer situation at a certain pH. How does the pH change when we add some base, some strong base? So before the reaction, remember, it was equimolar. The 2 mole amounts equaled each other, so our pH was based upon the pKa. And this is something we saw in the calculations in the last set of notes. When the ratio of the acid to the base is equal to 1, then pH equals pKa. Since our Ka is 1 times 10 to the negative fifth, that means our pH starts out at 4.74, which was mentioned in the problem. So that's our starting pH because we're at an equimolar situation. It just equals pKa. But what's going to happen next is we partially neutralize it. And what we really need to look at is that neutralization from a particle point of view. And this is going to feel a little bit like what we did with icebox. Now, first you need to understand it's a 1-to-1 stoichiometry, and we're adding 0.02 moles of NaOH. Now, before we had a certain amount of acid and a certain amount of its conjugate base, and those amounts are going to change here. And through neutralization, you need to understand that one always becomes the other. So originally we had 0.300 moles of each, and now we're adding 0.02 moles of OH minus to the situation. And you need to get that in our neutralization reaction, which is what we're looking at here. So this is not the equilibrium reaction. This is the neutralization of our acetic acid to make acetate. It's a 1-to-1-to-1 stoichiometry. So at the end here, remember we said it was safe to assume that we always use up all of our strong. In this case, we're going to get down to 0 from 0.020 moles, which means exactly 0.020 moles is how much our acetic acid went down. And by the 1-to-1 stoichiometry, how much the acetic acid goes down is how much the acetate goes up. So doing the math here is a fairly simple process when we're in moles. And remember, we have to be in moles to do this calculation because we're looking at a chemical reaction, and that happens on a particle level or a mole level. And notice that however much one goes down in a buffer situation, the other goes up by the same amount every single time because one is being converted into the other. And it doesn't matter which one we're neutralizing. However much one goes down, the other is going to go up. Now, once we have these new mole amounts, we're ready to do the equilibrium part. So remember, this is our equilibrium reaction. We've got acetic acid in water, and we have significant amounts of the acetic acid as well as its conjugate base acetate. Now, from that, we can write the Ka expression. From that Ka expression, we can solve it for H3O+. If we take the negative log of that, we get the pH. So we did this in the last slide, or the last set of notes, so I'm not going to go through that whole process again, but remember what we're doing here is solving the Ka expression for H3O plus, and then to get pH, taking the negative log of it. Well, we just calculated what our new mole amounts are for acid and base, and they were in 1 liters of solution, so we know that the molarity is going to be 0.280 and 0.320 molar. Notice we went from mole amounts to concentrations here because that's what's supposed to be in our equilibrium expression is equilibrium concentrations. Now, one mention, if we're not at 1 liter, then these amounts are going to change, but it's important to note to simplify things that whether we change to molarity or leave it in moles, the ratio is still going to be the same. So while the numbers change when we go to a molarity, the ratio isn't. So really you don't need to worry about changing your mole amounts into molarity amounts. Just leave them as mole amounts and it's perfectly fine. You just need to remember your acid goes up top and your base goes on bottom. And the base in this case is our acetate. Once you plug those in and calculate, you now find your new pH. And notice it didn't change all that much. So even though we added a strong base, and you would think that would dramatically change the pH after adding a strong base, it only changed it a small amount because of the buffer system. And that's really all we're looking at in the second set of notes. Or I should say the second set of notes from section 17.2.